the wavelengths. So how do we differentiate this? So when we capture the data, we capture everything together, or we may miss something, maybe deliberately or unknowingly. So in order to get the data within a consistent wavelengths, we have to do filtering. So first let us define some terms associated with filtering. So the real surface is the surface limiting the body and separating it from the surrounding medium. So this is the definition as per ISO 428 and so on. So because the surface always has a layer of oil or water vapor on it. So we are not considering that as the surface, we are considering only the body as the surface. Surface profile. So the profile that results from the intersection of the real surface by a specified plane. So if you imagine a plane cutting the surface, so the intersection of the surface with the plane, so that will show a profile. So that is the ideal surface profile. So this is what that we are trying to get. This is our aim, to get the correct surface profile. So there is a condition that this plane should be perpendicular to the direction of layer. Okay, so we have to cut the surface such that the plane is perpendicular to the direction of the layer. So we have an interesting experience 2 years back. So since we didn't have a 3D roughness at the time, roughness instrument at the time. So and Anna University, they have recently purchased one instrument of this Taylor Robson, CCH. So I sent some samples to compare stylus type roughness with optical roughness. And unfortunately, we couldn't get any correlation between the two values. And then later I analyzed the data and saw that they were not doing this. They were not taking the direction perpendicular to the plane. Unfortunately, it is operated by our just research scholars who don't know really about surface finish measurement, etc. So all the values were incorrect. So what is lay? Lay is the direction of the predominant surface pattern. So we have seen the specification of surface area. What are the different types of radial lay, perpendicular to the surface of the point, what the lay can be specified by the side, the random lay, etc. So if direction of lay is important for a function, it should be specified in the column. So which direction the lines of the lay should be there? If it is important function, then the designer has to mention that. It's a responsibility of the designer. So we have seen how it is specified. So what happens if we measure at a different angle? So suppose this is the surface. So this is the time and the elevation. So if this is the correct wavelength, the wavelength between two corresponding points. And so this is the direction of the ray. So for example, in shaping, I don't know whether you have done shaping, but in the lathe it will be along the circumference you can see lines on the surface. So these lines are the lathe. So this direction is the lathe. So if we cut the surface at an angle to this lathe, it should be perpendicular. If it is at a different angle, then the wavelength will change, the apparent wavelength will change. And of course, when we do filtering, what is the wavelength that we capture and what will change. If we choose a different wavelength, so the wavelength shown now will be different. Okay, so that is about surface profile. So surface profile is the ideal profile that we are trying to achieve. Trace profile. So locus of the center of a stylus tip, which features an ideal geometrical form, conical and spherical tip, and nominal dimensions with nominal tracing force as it traverses the surface within the intersection plane. So, of course, these definitions are all with respect to the stylus type instrument because that is the most popular, most widely used in industry. Whereas this interferometric type instruments are all very costly, of the order of 1 crore or so. So our required machines are costing around more than 1 crore because we bought so many mounting tables, etc., so many other features. So that is very costly. So nobody uses the industry. Just we try to get the cheapest instrument for the application. So of course, the requirement of getting a 3-dimensional parameter has not yet come up. So that is still under research stage. Whereas 2-dimensional surface parameters are well established. Okay. So the trace profile. So surface profile is ideal, the section between the plane and the surface. Whereas the trace profile is what is the profile traced by the stylus, an ideal stylus. So using a conical, the spherical tip, and nominal dimensions, the standard dimensions. So you don't consider any wear and all. That is a trace profile with nominal tracing force as it traverses the surface within the intersection plane. So that is the traced profile. So this is what we are going to get from an ideal instrument. A real instrument, again, there will be variations because of the stylus will wear out, forces may not be controlled. During traverse, there could be some vibrations, etc. Okay. But anyway, trace profile is the ideal that we want to get. Reference profile. So when we move the stylus on the workpiece, the trace on which the probe is moved within the intersection plane along the guide. So the stylus is pulled. So it needs some reference. With reference to what? You can move it at various angles. You are keeping it on some reference object and is pulled. So that is a guide. So whatever is the shape of that profile, that is called the reference profile. If you are measuring straight surface, usually it is a straight guide only. But in some applications, like you want to measure the surface finished over a gear tip, then you may have a guide which is of involute profile, etc. Okay, so this is reference profile. So reference profile, nowadays we are having two options. So the olden days, till about 2000 or so, we were using this type of instrument. So this is the stylus. The stylus movement is measured with respect to a skid. So we have a skid of much larger radius, at least 10 times bigger than this. And the skid is made to move over the surface, just float over the surface. And the deviations of the stylus are measured with respect to this skid. So since the skid is very large radius, it will just skim over the peaks of the surface. And we can measure the depths using this stylus. So this is the scripted type instrument, which was the only instrument available for quite a long time. Only last 2000. Okay, that's that time we also purchased this type of an instrument. So nowadays, okay, in 2000, 90s, this type of instruments was developed, where the stylus can be moved with reference to an external data, a reference data. Okay, so this is perfectly straight. So with respect to a perfect straight line, we can measure the deviations. Whereas here, we are measuring the deviations with respect to the motion of the skid. Where the skid itself will be moving up and down. So both the slight motion. But of course, it's very long waving, so it's not practically it does not make much of a difference. But theoretically, of course, we can say that this is the correct read. Okay, so that's why we purchased the second instrument, which is having the facility of skidless data. So total profile, digital form of the trace profile relative to the reference profile. So trace profile is what we measure in the instrument, and then the deviations of the trace profile with respect to the reference profile is converted to digital form, and that is called the total profile. So this is what we are getting before we do any filtering. So now we apply the filters to separate out roughness, waviness, and form. So profile filter is a filter which separates profiles into long wave and short wave components. So this is just a definition of a profile filter. So as you are seeing, nowadays we are all using only digitized data. The digitized data is mathematically filtered into short and wave, long wave components. So basically, we convert into Fourier series, and the wavelengths, long wavelengths, or whatever we want to filter out is filter. Filter quality. So ideally, if you specify a filter, say this lambda c is the filter cutoff. So lambda c is cutoff. So ideal filter should filter out all wavelengths below this, it should be filtered out. All wavelengths above this should be transmitted. So ideally, we should get a characteristic like this, a vertical line. So let's say if this filter is for a wavelength of say 0.8 mm. So all wavelengths below 0.8 mm should be filtered out. All wavelengths above 0.8 mm should be filtered out. But such an ideal characteristic is practically impossible. So real characteristics will always have some smooth curve like this. And if the filter is a bad quality, filter, you have a very long curve. So it will be transmitting a lot of the shorter wavelengths and filtering out a lot of the large wavelengths. So the quality of the filter, so what is the nature of this filter, also has to be controlled. Then only we can get comparable measurements between different instruments. So earlier, different companies used to adopt different filters, and that led to, so if you are measuring in one instrument, you get one value. You are measuring in another instrument of another way, you get a totally different value, because different manufacturers are using different filters. And in the 70s or so, these filters were standardized. So this is ISO, this published in 1996. I think in the 90s also it was standardized. So according to ISO, the filter characteristic should be Gaussian in shape. So that is normal distribution is a cumulative normal distribution. So transmission percentage. So roughness filter is shown in blue. So this is a roughness filter. That means the roughness is filtered out and waviness is transmitted. Waviness filter wet. So that means for this curve, so this is 2500 micron. So filter is above, wavelengths above 2500 micron are all filtered out. But it's not exactly, it is not vertical, but the shape is, so we have to standardize the shape. So every company has to obtain this shape. So this was standardized. The Gaussian filter was defined as the default filter. If you don't mention anything in the specification, then the Gaussian filter has to be used. Okay, so any question on this? So general principles of filtering we are seeing. Now we have different types of filters to get different profiles. So depending on the wavelength, roughness and waviness is separated out by lambda c. So that is the filter cutoff. So of course this is should be Gaussian shape, because my drawing is not so perfectly of Gaussian shape. Okay, so roughness profile. So the stylus radius because it has to have a finite radius. So wavelengths which are much smaller than the stylus radius cannot be captured. So this portion is blank. So that's why it is 0% from here to lambda s. So that is corresponding to the wavelength of the stylus radius. And above that, slowly transmits more and more till this region. Everything is transmitted. And then here we have to filter out through filters. So this portion we are not able to capture because of the limitation of our instruments. So that is the stylus radius. So stylus radius, generally we have 2 micron radius, 5 micron radius. So if you are using 5 micron, then this is okay. If you are using 2 micron, then some more data from here is captured. Then we have to use a filter if you got the very low wavelength source. So the variance between lambda s and lambda c is considered as part of the roughness profile, and variance between lambda c and lambda f. So greater than lambda f is considered former. It is not considered waviness. So waviness profile consists of variance between lambda c and lambda f. So ideally it should be exact, but practically it will be a smooth Gaussian curve like this. Okay. So lambda is profile filter is the filter which defines the intersection between roughness and the even shorter wave components present in the surface. So ideally, we should capture and we should filter out wavelengths smaller than lambda s. Lambda c profile filter is the filter which defines the intersection between the roughness and waviness components. Okay, so this is the critical filter because in practice, our instrument usually captures roughness and waviness. So usually the stylus instruments, they are not able to capture former because the wavelength of former is much higher. Okay, so generally we are interested in capturing roughness and waviness, and we want to eliminate waviness. So for that we select a suitable filter. So lambda c defines the difference between roughness and waviness. And lambda f profile filter is the filter which defines the intersection between the waviness and the even longer wave components present in the surface. So that is actually former. But we don't know because it cannot be called form because it don't have full that much wavelength data which you are generally not able to capture. Okay, so these three filters define or separate roughness and waviness. So cutoff for measurement. That is the limiting wavelength specified to remove waviness. So it should be short enough to exclude irrelevant long wavelengths and long enough to include enough texture for meaningful results. So we have to choose a proper cutoff so that it is the necessary wavelengths are included. So the ISO has standardized the cutoffs to be so that different manufacturers all from the options given on the machine should correspond to the same wavelengths. So 0.08, 0.25, 0.8, 2.5, 8 mm. So these are the standard cutoffs specified by ISO for surface structure measurement. So, and if nothing is mentioned, 0.8 mm is the default. So that is the middle value is the default. So if not mentioned, the cutoff should be 0.8 mm. Okay, so that is the specification for cutoff. So what happens when you change the cutoff? So the same surface, so measured profile without electrical filter. So in the olden days, it was not digital filtering. When we started developing measuring instruments, surface measuring instruments, so microprocessors and all were not there. So they used to do electronic filtering or electrical filtering using a capacitance and an inductance. Okay, so RC filter, XC filter, etc. used to be there. So earlier days we used to have that only. So the first machine is used to. So the filtering was not controllable. Just have to connect it electronically, and whatever the output we get will be either of some certain wavelengths. We can't which is not mathematically correct. Because nowadays everybody does the analysis mathematically. So this is a profile without electrical filtering. Then with 0.8 mm cutoff. So this is 1 mm. So wavelengths close to this are filtered out. So you can see this is one wave here. Gauss wavelength. So that is filtered out. So now that this Gauss wavelength is not here. Then what will happen? The amplitude also comes down. So with 0.8 mm cutoff, average. So this is the average height of irregularities. We will define that later. So it is around 3.5 to 4.2 micron with 0.8 mm cutoff. That means wavelengths above 0.8 mm are cut off. And with 0.25 mm cutoff, that is wavelengths above 0.25 mm cutoff, the value of RA is reduced even further, 1.8 to 2.2 micron. See here, this sharp peak, here the amplitude is high because this wavelength is very small. But long wavelength, more than 0.25 and all is removed. And with 0.08 mm cutoff, the value of RA gets reduced to 0.95 to 1.05. Okay, so this is one way which inspectors will trick. Sometimes external customers will come for inspection and all. So if the surface is slightly high, what they do is they change this cutoff. So if you reduce the cutoff, the value of RA you obtain for the instrument also gets reduced. Okay, so you can manipulate results. So you should know what is the meaning of cutoff. What cutoff we are using for surface finish measurement is very important. So the same surface, if you use 0.8 cutoff, you get RA 3.5 to 4.2. If you use 0.08 cutoff, you get RA 0.95 to 1.05. And okay, recently we had interesting so we were asked to measure surface tension of some components from BTK Trivandrum. So they are making walls for artificial walls for heart surgery. And so they have developed a new process to polish the seating surface, and they wanted to measure the surface roughness. And usually they used to get it measured at they have this optical profiler. Because they were busy, they were getting delayed the approaches so that we can do it. Then we measured the aluminum instrument. Of course, we had some problems. We were not, because they did not specify the cutoff to be used. So when we measured the different times, we got different readings. So first I measured with the help of another person, we got some readings. Then Dr. Deepak was measured, his research scholar was he measured and we got different readings. Because the main problem was that they did not specify the value of the cutoff. And I don't know. So I was not happy with the so I did not give a report. So finally, he sent a report and afterwards they did not say anything. So but when we asked them what cutoff should be used, that is the motive. They don't know what is cutoff. So they were the person, the biologist, is controlling quality control chief at the hardware. So field was not knowing about what is cutoff, etc. So because the development was done by the CT and it was the technology was transferred to this DTK for the manufacturer. So they don't know about what is all this. So and then because the process was very slow, they made some improvements that they want to check whether the surface is better or not. But we could not give any conclusive result because the specifications are not there. So that is the first thing in measurement. What is to be measured should be clearly defined. If the customer does not know what is the cutoff to be used, what can we do? So depending on the cutoff used, so again, Alicona we can use various magnifications. If you go for very large magnifications, automatically okay, the range will be very small. The range of measurement will be very small, and only small cutoffs can be applied. Large cutoffs cannot be applied. So if you use large cutoffs, the RI will be roughness will be very high. If you use very small cutoffs, so if you use large magnification, automatically the RI values will be very small. So anyway, we tried to explain to them, but they just wanted to get some report. Is it okay or not okay? They're not interested in learning. So lifelong learning, I was just mentioning. So that is the academic attitude. In industry, the people are not really bothered about what is correct or not correct. As academicians, we always worry about what is the ideal correct way to measure, etc. Okay, so with that, we'll conclude for the day. That's the problem with the choosing the cutoff for surface roughness measurement. Okay, so the primary profile is a total profile after application of a short wavelength filter lambda s, final stylus or standard filter. So the mean line is obtained by fitting a least squares line of nominal form through the primary profile. So roughness profile. So now we have to, primary profile is the total data after removing wavelength smaller than lambda s. This is automatically done. So now we have to split out into roughness, waviness, and formula. So formula also we are not capturing mostly, but anyway, so lambda c when you filter, all wavelengths above lambda c is removed. The profile derived from the primary profile is suppressing the long wave component which is the profile to lambda c. So primary profile is already not having wavelengths smaller than lambda s. All wavelengths greater than lambda c is filtered by its filter. What is remaining is roughness. So if this primary profile, you filter out the small wavelength portion, profile derived by the subsequent application of the profile filter lambda f and the profile filter lambda c to the primary profile, suppressing the long wave component using profile filter lambda c. So wavelengths larger than lambda c, suppressed, so they are smaller than lambda c are removed, and larger than lambda f are also removed. Then what is remaining is waviness profile. Okay, so the language in the standard is complex. Profile derived by the subsequent application of profile lambda f. So first you remove wavelengths greater than lambda f, then apply lambda c to the profile, primary profile. So suppressing the long wave component using the profile filter lambda c. So wavelengths greater than, smaller than lambda c are also suppressed. So remaining is waviness profile. So decomposition is given in wavelength. So what we get from the instrument, so there will be some misalignment between the working surface and the guiding lens surface. So first we filter line of d square, and what we get is the primary profile. And then the form long wavelengths are removed, and we can split into waviness and roughness. Oh, sorry, yeah, this is the raw profile. This is from this, if you remove this tilt, the form, what we get is primary profile. And from primary profile, if you split the waviness filter, the filter out waviness, what we get is roughness. If you accept waviness, what we get is the waviness filter. Okay, so the raw profile, after removing tilt, you get primary profile. And from primary profile, by using the lambda c, we get waviness profile and roughness. So how is all this filtering done? So that is using a discrete Fourier transform. So this is obtained a MATLAB clone. So it works just like MATLAB, but it is free and open source. Okay. So this is a code to generate the sinusoidal profile. So this is the surface. It's how did we obtain this? Actually, it consists of two waves. X1, no, Z1 and Z2 with two different amplitudes and two different frequencies. So Z1 is 1 into sine 2 pi x by 2. Z2 is 0.5 into sine 2 pi into x by 0.5. So this is amplitude 1 micron, amplitude 0.5 micron, greater than 0.5 micron. So the combination we get this. So this is how a measured surface chart looks like. Now how do we separate this out? So for that we have another code. So we convert this into a Fourier series. So then what is a Fourier series? Will be a series of sine waves. This is the first the code to generate the surface. And then second code to split this into two. This is the Fourier transform. So this consists of, so we know that it's a combination of two sine waves. So we are able to get that. So this is the amplitude of first wave. This is the amplitude of the second wave. So this is the two different waves, two different amplitudes. So this is what we are doing in filtering. So this is the original mix-up of two waves. So by using a filter, you can get back the different wavelengths and this is all filtering of the surface finish profile. Okay, so those who are interested in studying detail. So now we come to various roughness parameters. So once we split the primary profile into roughness profile and waviness profile, we can calculate parameters on either primary profile or roughness profile or waviness profile. Okay. Accordingly, parameters based on primary profile are denoted by the letter P, roughness profile are denoted by the letter R, waviness profile is denoted by the letter W. Okay. So the first letter stands for the profile which you are choosing to calculate the parameter. So this is the total process, how we analyze the surface. So we start with the real surface. So what we get is theoretically what we should get is the surface. And then there are some losses, bandwidth, stylus tip, sampling speed, etc. So we get the trace profile. So perfect stylus will give the theoretically correct trace profile, but actually there will be something missing because we cannot capture data below the stylus and the stylus shape and some difference, or that will show some deviation. So what we get is the trace profile. So that is the extracted profile after sampling X and digitizing in Y. So that is the total profile. Trace profile is continuous. So digital form is called the total profile. Then form removable by fitting with nominal strip. So also lambda is filter cut off. Very short wavelengths are removed out. If it is not already done, and if you are using very small radius stylus, then this has to be an extra. First we remove this lambda s. What we get is the primary profile. So if you calculate parameters from this primary profile, they are called PQ, PSK, PE, etc. All these are primary parameters. The primary profile you apply lambda c filter. So all wavelengths below lambda c is removed. It's waviness profile. All wavelengths above lambda c is removed. We get its roughness profile. So from roughness profile we calculate R parameters. From waviness profile we calculate W parameters. Okay, so this is the flowchart of the computation of a stylus type profilometer. Okay, so now we come to the computational part. How do we calculate the parameter? What is this RA? What is RP? What is it? So for that, some more terms have to be defined. So what is the sampling length in R? So the length in the direction of the x-axis used for identifying the characteristics characterizing the profile of the evaluation is called sampling length. How much length we are using to characterize the values? Okay, that is sampling length. The actual sampling and actual measurement length is slightly different. So what happens when you choose different sampling lengths? This is the surface. If you choose only a small region, so you get only the amplitude will be limited to this. This large amplitude thing is totally missed. So that's why all these are connected. Cutoff length, sampling length, all these are connected. Evaluation length, so total length in the x-axis used for evaluation. So this is different from sampling length because one evaluation length usually consists of several consecutive sampling lengths. So ISO 4287, but it's 5 sampling lengths of evaluation. So otherwise, it would be simple RS. So if you simply say RA, it means RA from 5 sampling lengths. If you are determining from 6 sampling lengths, you should say RA6. If you are determining RT from 2 sampling lengths, you should say RT2. Okay. So already we are seeing the drawing symbol and how this is noted in the symbol. Okay. So sampling length, evaluation. Now the total traverse length is the distance traversed by the stylus. So this is slightly more than the evaluation length, right? So total length of surface traversed by making measurement is greater than the evaluation length. Because when you are starting from stage first, so there is some acceleration. In order to get good reproducibility, the fidelity in the characteristic of the stylus, we would prefer to move it at constant speed. So initially that accelerating time and the deceleration time both at the end are excluded. So that's why this total traverse length is slightly more. So there is a more travel at start and end to avoid the region of acceleration and deceleration. So this is the total traverse length. This is evaluation length. The evaluation length is normally 5 sampling lengths. or it can be any sample length as specified by the designer. Okay, so this is the sampling. So each calculation is done based on the sampling length, and the average for several sampling lengths is taken as the parameter array. Array or whatever, the parameter is based on the average of all the values in the evaluation. Okay, so this was the method adopted by Taylor Hobson in the beginning, and that has become the default standard. Okay, so how do we decide cutoff? So we have learned that it's very important to select the proper cutoff. So there are some recommendations. So these are applicable if the designer has not specified the cutoff. So once again, first we have to decide whether the surface is a periodic type or a non-periodic type. So first we have to visually examine the surface. What are the lines on the surface? Is it a periodic surface or non-periodic surface? So for non-periodic surface, the procedure is as follows. First determine R, not determine, estimate R. You think what will be the on the spacing, and we can use a comparison scale, etc. And decide what is the approximate R. Then for that array, there is a table in the next slide. These are recommended values of cutoff from the table. So select recommended cutoff from table and measure. If obtained roughness is within recommended range, try a smaller cutoff. So if we get to roughness same as the recommended range, within the recommended range, you can try a smaller cutoff. So if you still it is within the recommended range, you can try a smaller, still smaller cutoff. So the final value what you get is the treated as the roughness. Now this is the table. So RA very fine cutoff is 0.08. So LR is the sampling length, LN is the evaluation length. And here sampling length is same as the cutoff. 0.02 to 0.1, sampling length is 0.25. 0.1 to 2, RA is 0.1 to 2, sampling length should be 0.8. So this is the normally in most we get RA around 0.1 to 2. The cutoff is 0.1. But if you are using grinding and all, the cutoff comes down below 0.1, then you have to choose a smaller length of cutoff. So, but if you initially itself you choose 0.25, you will get a lower value of R. So that is the problem with that measurement area. So if you expect only 0.1, start with here, you get value here. Okay, that is the. Then that's why we have to have some method of designer. Next is that the designer specify what cutoff to be used. Okay, so 5 sampling lengths is equal to the evaluation length. So that is a procedure for non-periodic surfaces. And for periodic surfaces, again, start with an estimation of RSM. What is RSM? Again, we have to learn next topic. So that is spacing, mean spacing. RSM stands for mean spacing. So spacing is actually measured along the x-axis, whereas RA is measured along the z-axis. So estimate RSM, select recommended cutoff from table below, next slide, and measure. If obtained RSM indicates smaller or larger cutoff, choose that. Otherwise, return. So previously, only if it was smaller, we used to change. Here, if it is smaller or larger, you have to choose that. So initially, you have to start with small cutoff, and then obtained RSM is, so now it is based on RSM. For periodic surfaces, RSM decides the cutoff. So that's why I have shown the photograph. I have marked the spacing between peaks. Okay, so the RSM is the mean spacing. So that defines the cutoff to be used. So if the mean spacing is large, then you have to use the corresponding cutoff as given in the table. Okay, so RSM is say around 0.4, then 0.13 to 0.4, sampling length is 0.8. So we should reduce to 0.5 only if RSM is smaller than this. But for both sample, that was not the case, so that's why choosing sample length smaller than 0.8 may not be correct. Okay, so we estimate RSM, find out the sample length, measure, and suppose the measured value is 0.25, that means then you have to choose for a different cutoff. Okay, measured value is here, or less than 0.13, choose sample length 0.5.